here to discuss with a colleague from Morocco and from the Maghreb and from abroad. So as Kader said, I work a lot in 2D materials and we work on silicene. And this is the topic that I will show you today. So I'm going to talk about the silicene and phosphorene new 2D materials. So this is the plan of my talk. I will introduce these 2D materials, and I will focus in the first part on silicene, and I switch to the phosphorene, and I will conclude. So before starting, I would like to start with this citation, which say that history does not repeat itself, but it does rhyme. And this is true in the life, but also in science, because we work a lot on carbon, silicon, germanium, and phosphorus. And now everybody is working on graphene, silicene, germanium, and phosphorene. So I will focus my talk on only silicene and phosphorene. And why scientists are interested to these 2D materials. As you know, we are now focusing on devices with high density of storage, which means that we have to reduce the size of this storage. And as you see here in research from 2015, we're working on device with 10 nanometer, and we're going to the 5 nanometer. So if we go further, we will have a problem with what we call Moore's law, because this law gives us somewhat the size of device versus the year. And here you can see the number of atoms if we take a silicon chain. And here we are in this part. So we will have a problem if we cannot reduce the size of our device. One thing that the new 2D material can do is to break this limit of Moore's law by using single 2D layers like silicene, graphene, etc. Why? Because these layers are only one atomic thick, so we will be in this region. So as you know, a lot of people work on graphene, and all the government, they put a lot of money on graphene, but until now, there is no really very practical device based on graphene. I'm talking about transistor point of view, because the graphene is metallic, and if you want to do transistor, we need to have a gap. So scientists focus their research on silicon, because silicon, we know how to dope it, we know how to manufacture it, and the actual nanotechnology is silicon-based. So if we can synthesize silicene, we'll solve the problem. The silicene has the same structure than graphene, but with silicon atoms. And if we look to the first scientist who works on the system, they are theorists. And here I show a few papers. The list is far to be exhaustive, because all this paper, they show that the silicene, if it exists, it will be stable, but it will be buckled, not like graphene. The second point is that the silicene, if it exists, it will be intrinsically stable, and it behaves like graphene from the electronic structure, which I show you here. Here I show you the band structure of silicene, and we can see here a linear dispersion like graphene, which means that electron here behaves like photons, which means that they have constant velocity. So if we can to synthesize this silicene, we will really break this lock. So the first measurements we did are done on silver 110. Here I show you the deposition of silicon on silver 111, and spontaneously the silicon formed this nanoribbon with 16 angstrom in size, and even we can have a low energy electron diffractometer, which show diffraction indicating that this structure is crystalline. And here we can see the unit cell of silver, and here the unit cell, which is 2x5, corresponding to the nanoribbon. As you know, the STM is really sensitive to electrons. So sometimes what we see does not correspond to atoms. So we did the atomic force microscopy in non-contact mode in the same area. This is the same area because we have an apparatus which allow us to get two information. We can get STM topography, and we can switch immediately in the same area, and we can get information about with the atomic force microscopy. And you can see here, you can see the same symmetry. We have the width of 16 angstrom, which means that the images done by STM are not affected by electronic effect. If we go further, here the STM image is recorded with the 0.35 nanoamperes. If we push the tip further to the surface, here for example is 3 nanoamperes, we can see some honeycomb-like here, which means that we are dealing with the synthesis of silicene. We did the same thing with IFM too. By increasing the frequency, we are working with the Keplers. We don't have a cantilever, we have Kepler's fork. And we can see more or less the same structure made by honeycombs. So from other groups, they start working on the same system. And here, for example, a paper which report that the growth of silicon on silver induce or miscible on silver, which means that the interaction between silicene and silver is strong. Another group show that silicon induce faceting of silver. If you deposit silicon at high temperature on silver, you start forming pyramid structures. Here I show you another group who claim that this nanoribbon I show you are formed by pentamers instead of hexagons. And at the same time, another group using EXAFS techniques. The EXAFS techniques is a technique that it can give us directly the exact interatomic distance. And they show that the silicene formed on silver 110 and 111 show honeycomb, and it has hexagonal structure, and the distance between silicon and silicon is 2.35 angstrom. So what happened now if we switch for silver, because silver 110 is anisotropic and we have lines. So if we switch to silver 111, which is isotrope, maybe we can get sheet of silicene. So this is what we obtain. When we deposit silicon on silver 111, we start by this structure. This is the first structure we have published before. And after that, other groups, and also in our group, we found that depending on the temperature of the substrate, we can get different structure. So each group published its structure, and he claimed that he discovered silicene for the first time. So in collaboration with our theoretists, and in particular Professor Kara, we explain all this structure. Here I show you just explanation. We start from the silver 111. Here, this is the crystallographic direction of silver 110. If we put a sheet of silicene on it, we can find some epitaxy, I show you here, which correspond to the 4x4, and this is the simulated STM image. Now, if we keep this sheet and we just turn it, we can find another epitaxy, which is root 13 by root 13, and here, this is the simulated STM image. And if we continue turning the sheet, we will have this, and if we turn again, we'll have this one. And all this structure correspond to this. So we solve the problem. All this structure correspond to silicene sheet, but the silicene, when it rotates, some atoms are on top and others are down. So recently, another group report silicene transistor. They use the same technique that we have. They, instead of growing silicene on silver, they put silver on mica and they deposit silicene on it, and they cap it by alumina, and after that they flip the system and they make the drain and the source from the silver. And they got some results concerning the mobility and the concentration of carrier. However, the lifetime of the transistor was very short, which means that the silicene is reactive, and we should look to other methods to protect the silicene. But anyway, this result showed that the silicene can be integrated in industrial technology. So what is the future challenges? Because as I show you, we have a strong interaction between silicene and silver, and silver alters the electronic structure of silicene. So we should look to other surfaces, in particular insulating surfaces. And if we succeed to grow silicene on insulator, we can make some electrode, and we can make electronic measurement and devices. So we think about growing sodium chloride thin film on silver 110, and the idea is to deposit silicene on this insulator in order to decouple the electronic structure of silicene from the silver. This is what he did. I will show you briefly the lead measurement. This is the lead corresponding to the silver 110, and after deposition of 1 molar of sodium chloride, we have this structure which is called 4x1 because we have spots corresponding to by 4, and here we don't have spot in this direction. And this is the explanation of this structure, which means that 4 distance of silver in this direction are equal to 1.15 nanometer. It corresponds exactly to 3 parameters of sodium chloride, which is 1.19 nanometer. If we look to the surface with STM, here, this is the surface of silver 110. This is atomic steps of silver. And we deposit sodium chloride. We made a systematic study in order to control the size of this insulator layer, and we see we can have a size more than 160 nanometer. On this sodium chloride, if you can see here, we have the atomic resolution, we have silver here, and we have the atomic resolution of sodium chloride. After deposition of silicon on sodium chloride, here this lead corresponds to growth of 1 molar of sodium chloride on silver. After deposition of silicon, we have new order, which is here by 3 and here by 4. It's different from the order of sodium chloride. It's always difficult to see the order by lead, but in the real space, if you go to the real space, here, this is the island I show you of sodium chloride, but on top of it, we have silicon. If we can make some zoom on this zone, we can observe that we have some honeycomb structure, all oriented in 2D. And we can see here the unit cell, which corresponds exactly to the unit cell deduced from the lead pattern. So we have some spot, as I told before. With this term, is difficult to see that this is silicon, and it's difficult to see that there is no interaction with silver, and etc. So what we did photoemission spectroscopy in synchrotron radiation. The photoemission spectroscopy can give us exactly the environment of silicon, or silver, or sodium chloride. Here I show you the core level of chlorine, and sodium. And here we can see just a double, which we can fit only with 1 component. The same thing for sodium, we have only 1 component. And in XPS, if you have 1 component, this means that we have one and unique chemical environment, which means that the sodium have chlor-like neighbors and vice versa. We did the same thing for silicon. This is silicon 2p. We also fit this spectrum with only 1 component, which means that silicon have only 1 environment, silicon with silicon. We did many techniques, and we use EXAFS. As I told before, EXAFS is unique technique because it gives us exactly the interatomic distance of your material. And here I show you here, this is proportional to the coefficient of adsorption. What we did, we excite the silicon key edge with the energy, and we plot the variation of the coefficient of absorption versus the energy. And here I show you versus the radial distance for bulk silicon with blue and with silicene on sodium chloride on silver. And what you can see, the two pictures are quite similar, in particular this distance and this distance, which correspond exactly to 2.35 and 3.83 angstrom, which are the first numbers and second numbers. We can note that there is a shift here compared to this value, but this shift is due to the exact techniques. So we can deduce that we are dealing with pure silicene layer on sodium chloride. Again, with the help with the theoretists, we show that one silicene layer, shown here by blue atoms, is stable when it's deposited on sodium chloride, and we show that the silicene shows some buckling. It's not flat like graphene. So now I will switch to the phosphorene. As I told before, the graphene has problem because it's semi-metallic. It doesn't have a gap. For phosphorene, its properties are much suitable for devices because the band gap of phosphorene can vary from 0.3 to 2 angstrom to 2 electrovolt, depending on the thickness of phosphorene. If you have one more layer of phosphorene, the gap is around 2 eV, and if you have a thicker phosphorene, we will have 0.3 electrovolt. And also, the mobility is very high. It's 5,200 at room temperature, which means that the system is very useful if you can make devices, because we have band gap, we have mobility, and even the on-off ratio is very high, which is good for transistors. But if we look to the synthesis of phosphorene, what we have actually now, most of the study report only synthesis by exfoliation, mechanical exfoliation, chemical exfoliation. If we want to integrate phosphorene in industry, we should grow it by chemical vapor deposition or by epitaxy. So the first paper published on this paper, on this field, it's in 2016. It is the same time that we have this result, and we lose time. And they publish this result, and they call it the epitaxy growth of single layer blue phosphorene. And their STM image shows some triangles with 6 protrusion, and this is the simulation. And what is the blue phosphorene? The blue phosphorene is only a new allotrope structure of black phosphorus. If we look here, we have a side view of black phosphorus, and here the top view. And if we want to go from the black to the blue, we just have to make a dislocation. This dimer, we put it here, it will be here, and etc. And we will have a zigzag structure. And from top view, we will have a honeycomb structure like graphene or silicene. So we grow phosphorene on gold. Here I show you the lead pattern of the gold 111. We have hexagonal structure, and we have some satellites characteristic to the gold, to the clean gold. After deposition of phosphorene, we got a new order, which is by 5, which means that our structure in the real space is five times larger than unit cell of the gold, which means that unit cell is 1.44 nanometer. With STM, we got this image, and you can see that the structure is this. It corresponds exactly to the by 5. This is the line profile done around this dimer, and we can deduce the unit cell of 1.44 nanometer corresponding to the value deduced from need. And we can see that this structure is made only by trimers, not 6 atoms, which contradict the results published by the other group. With the help of the theorists, we simulate this image. This is the experiment. This is the model. And the model consists of one layer of blue phosphorene, and on top of it, we have 3 atoms of phosphorus. And here we can see the simulated STM image, which really it's in good agreement with the experiment. From electronic property, we studied the core level of phosphorene, and I show you before here If you remember, for silicon, we have only one component. For phosphorene, we have two components, S1 and S2. So S1 corresponds to the chemical environment phosphorus, but the S2 corresponds to environment phosphorus with gold. We did ARPES, angular resolved photoemission spectroscopy. We measure only the density, the electronic density in the valence band. And if we see here, we can see two contrasts. The contrast here is weaker than here, which means that in this region, we are in the gap of the phosphorene, and only we see the state of gold. Beyond 0.8 electrovolt, the contrast is much stronger, which means that we have the two contribution of phosphorene and gold. And I show you here the integrated image. This is the same thing, but we integrate everything here, with the energy, and we can see exactly this variation, and we deduce a band gap of at least of 0.8 electrovolt. We cannot measure the empty state because we are using XPS. We are sensitive only to the field state, but we have an idea about the band gap, which means that at least it will be equal to 0.8. So I hope I didn't take a lot of time. I conclude, I think the silicene, even the groups have a lot of problems to grow it. We start to grow it on insulator, which means that the integration of silicene is in the way. And for phosphorene, maybe the epitaxy of phosphorene on substrate will be useful if you want to integrate immediately phosphorene in industry. And I would like to thank all people who participated to this work, because this work was done within a consortium, people from our group in Orsay, from Soleil, where we did photoemission and ARPES, and also from Morocco, from mainly in Rabat and Marrakesh, and of course, Abdelkader Kara and IRSEC'18. And just before finishing, I would like to make an announcement. We have a tradition to organize a conference in Marrakesh each 2 years. In next June, we will organize the next edition. This is the fifth Euro-Mediterranean Conference on Materials and Renewable Energy. And the goal of this conference is to gather people coming from the north and the south of the Mediterranean. And the website will be open very soon. And of course, we are all welcome to this conference. Thank you very much.